Good evening, sir.
Good evening, good evening. Sir,
Yes.
last time you gave me that mail ID and that link, but you sent it on this, where you sent, but that I didn't get that actually.
On the meeting chat, actually, I
Uh-huh.
sent you.
But how to retract that?
No problem. Actually, I will give you it. So, can you give me your email ID? Then I will just send
Yeah,
you.
yeah,
Yeah.
yeah, yeah.
I'll just make a note of it.
Okay.
So, you please give me your email ID, and so you can actually.
Yes, Suhas.
Yeah.
Okay.
So, if you can post your email ID on the chat, I can.
Yeah, yeah. I'm doing the same thing.
Yeah. Yeah.
Please check, sir. Have you received?
Yeah. I'll note it. Sure, I will contact you later.
Thank you.
Thank you. So, sir, were you able to access the earlier recordings and all those
That
lectures?
also not possible. That also I haven't got actually.
Acha, okay.
Hmm.
So, you can actually go to the. So, I'll show you where to find all the recordings.
Hmm.
So, in the course page itself, you can actually just get access to
Yeah,
the.
yeah. At the course field, I think the last one, a video, something there.
So, I will just show you just a moment. I am
Ah,
sharing my screen.
acha.
Are you able to see the screen?
Yeah, yeah, yes.
So in the Swayam page, so you can go to the course page, Introduction to
Hmm.
Mechanical Vibration, and in that, so you have all these weekly things getting uploaded here, and in
Yes.
the bottom
Problem solving.
problem
Yes, yes,
solving
yes,
session, this one. So just
yes,
go to
yes.
this
Nice.
and click here to view the problem solving lectures, and
Hmm.
so here you will see this Google Sheet. In that
Yes,
you
yes,
will
yes.
get links to all the YouTube video recordings,
Yes,
and
yes, yes.
this is the drive folder which contains all the
Yeah. I
slides.
think I have seen. I have seen the first week video actually of yours.
Yeah, so,
Hmm. So I know that. I will get that now. Hmm?
yeah, sure. Sure, sir. Maybe then in 1 or 2 minutes we can maybe start with this week's session. So, so till that, like, sir, are there any questions or comments related to this week's content or last week's anything?
Last week, last week's session was very nice. Okay, and the thing is that uh, you solve the problems. You solve the problems. Okay, in detailing actually, which was difficult for us many times. Okay, to find the answer of that questions. So you solve the problem stepwise and explain it so nicely.
Sure, sir. Thank you. So, so hopefully we'll again continue with the same way in the next few sessions as well.
Hmm.
So this week we have content related to vibration measuring instruments.
Hmm.
Uh, So sir, you had any experience with vibration measurement, like experimental vibration measurement?
Yeah, yes.
Okay.
I'm using that FFT analyzer.
Okay.
Hmm.
Okay. So sir, how have you used that? Like in what uh, context have you used FFT?
The practical from practical for practical we have the practicals no of FFT analyzer.
Okay.
So finding out the natural frequency and that spectrums. Okay, how to read that spectrum. So that thing we take from that FFT analyzer basically.
Okay.
Hmm. The
Okay, sir.
peaks and peaks are there, na? N number of peaks are there. So at which frequency, how much is the amplitude and all that things
Right.
that we explain to the student.
Okay. Okay. So this is for
Mm.
BE level students.
Yes.
Okay. Okay. Great. Yeah, I think so. We have waited for long enough for other people. So hopefully, other people will also join as we progress. So I think we can get started with this week's session.
Yes.
So I am starting my screen sharing. So in this week as well, I have selected some questions which are similar to those which you will see in the assignments.
Hmm.
Uh, so when we can start uh, solving these questions,
Sir,
and
shall I suggest you something?
yeah,
Uh, we will see only the numericals because this theoretical part we will get from anywhere. Okay. The
right,
instrument that measures the displacement of vibrating body is called a seismometer.
right.
Okay, that we will do. Only the numericals if we have. So sometimes it's difficult to solve that numericals. Huh?
Yeah, sure,
So,
sure. So
so
anyway,
better,
yeah,
huh? So better to conduct or better to take that numericals here. Huh?
yeah, sure.
Hmm.
I just had one or two conceptual type of things.
Huh.
So this
Devise the
also
transfer value of physical variable into equivalent. This is transducer.
right. So yeah, so I like just to get started with the concept. I just had one or two questions like this. So then
Huh.
we will get started with the numericals.
FI kg mass.
So yeah, so we have this first question.
Huh.
Um, so a 5 kg mass is suspended in a box.
Huh.
So the box is shown over here in this figure,
Huh.
and so this so this whole that frame inside that. So we have this small mass which is suspended through a spring. So
Hmm.
its stiffness is given, its mass is given. So
Hmm.
then what will be the relative amplitude of that? So basically this setup as such forms the basis of all the vibration measurement instruments. So like all of these will be doing basically the same thing. So there will be some uh, so the instrument will be mounted on the so that base which we so let us say there is some vibrating body, and on top of that it will be mounted. So it will be basically measuring the relative displacement. So if we go to the free body diagrams of this system, and so if we draw the free body diagram of this mass, so let us say this undergoes a so the displacement as a function of time for this mass, let us say we call it as x of t, and this motion of the
Hmm.
base, let us say we call it as y of t.
Hmm.
So So then, so there will be basically this spring force that will be acting on this. So considering that this x is measured with respect to the equilibrium position, so then the weight will not be a dynamic force in that case. So then it will be mainly the spring force. So now this uh, since this whole base and this frame also is moving along with this thing, so this top part of this box will also be moving with yt. So basically the spring, so if we see that, so its upper end is moving as y of t and its lower end is moving with x of t, right? So then what will be the spring force? So it will be k into x minus y or y minus x, whatever, like depending on uh, whatever the direction that we choose. So then if we then write the equation of motion, so then if we write the equation of motion of
mx
this
double dot
mx double dot,
plus
so here let us say if we assume that, let us say y is greater than x for this, so then the spring force is so then let us say the spring force is tensile in nature. So spring is under tension, so then it will be y minus x.
y minus,
So
correct.
then mx double dot is ky minus x, right? Right. So then now the this measuring instrument, so it is asked that what will be the relative amplitude. So relative amplitude will be, let us say, x minus y, so that we call, let us say, as z of t. Okay, so then x dot minus y dot will be z dot, and x double dot minus y double dot will be z double dot. So then, so x double dot we can write it as y double dot plus z double dot. So it can be written as excuse me, is equal to kz minus kz, sorry. So mz double dot plus kz is equal to minus my double dot. So this is the equation of motion, so in terms of the relative amplitude. So basically this is the relative motion z. So now if we yeah, so let's just rewrite our equation, mz double dot plus kz is equal to minus my double dot. So then if we use our earlier like approach of how to solve this, like get the particular solution, so like we can assume a solution of the form for y, like y is equal to y sin omega t. So then z will be something of the form z sin omega t minus phi. So or we can also use that like y is equal to something y e to the power uh, j omega t, and z is equal to some z into e raised to power j omega t, where y and z can be like any complex numbers. So we can use any of these methods, and then we will get basically minus m omega square z plus k z into, so let us say if we use this into sine omega t minus phi is minus m y double dot sine omega t. So we get basically the expression in terms of, so z, so we will get uh, so we will get an expression of this form, omega squared y upon uh, k minus m omega square uh, so we have to basically find out the relative amplitude over here. So we have been given that like omega is, so here we have been given that y is equal to y sine of 8t. So omega is 8, and we have been given that k is 8000. So this is in terms of centimeter. K is 8000 Newton per meter, and mass is 5 kg. So we can find omega n is root k by n, which is root 8000 by 5, which is root 1600, which is 40 radian per second. So now if we substitute this in terms of uh, all the given data, so we will get z is m omega square y upon k minus m omega square, which is 5 into 8 square into uh, so y, which is basically 1, and k is 8000 minus mass is 5 into omega is 8. So it should be 1 upon, so 8000 upon 5, 5 into 8 into 8 minus 1. So it should be something so what will be the value of this expression?
Right. Right.
1 by 24. So the value of z will be 1 by 24, which is about 0.0417 centimeter, right? So if we check the options, so it will be this will be the correct answer. So any doubts on this question? So if we actually consider any, in general, any damped spring mass system, and use the same approach with the same kind of a system. So if we just consider a spring mass damper as well, like here there was no damper in this question. So if we consider the same setup and consider damping as well, so then the value of z in terms of y will be something like this. So here we, as in r is basically omega by omega n. So and if we try to plot this value of z by y, so basically z is the relative displacement and y is the amplitude of the base motion. So it's the same setup like this. So we have a spring and then a damper, and let us say we have a mass m. So then let us say this is the motion of the base y, the motion of the mass is, let us say, x. So then that is how we will get basically the nature of the plot. So so if we want to use this setup as a vibration measuring instrument, so if we want to measure the displacement, then what will be being measured is basically z, or the relative displacement. So if the relative displacement has to be close to whatever the base displacement, so then z by y should be nearly 1 if we want to use this as a vibrometer. So then, so in this plot, we will be basically mainly interested in the range where omega by omega n is greater than or equal to 3. So then in this range it can be used as a vibrometer or seismometer, whatever we call it. So then whatever is being measured, it will be proportional to the displacement of the base or whatever object on which it is being mounted. So then in this, so for that omega by omega n should be greater than or equal to 3. So for that omega n should be small, or basically the natural frequency should be small. So omega n, which is basically root k by m. So for omega n or natural frequency to be small, we have to have a soft spring and a huge mass. So it will be like something bulky, but that's how basically the vibrometer ideally should be. So this is about the vibrometer part. So then if we again want to use this as an accelerometer, so we will see that later. So for accelerometer, then the whatever displacement of the relative displacement, it should be proportional to the acceleration of the base. So that's how we can have that. So for that, it should be basically the omega by omega n value should be much smaller than 1 for that. Yeah, so this question is again the same thing, like basically the design criteria for the vibrometer. So it's basically just what I mentioned. So omega by omega n should be greater than or equal to 3. Yeah. So we have a numerical example related to vibrometers. So it is given that the vibrometer shows a 2% error in the measurement, and its natural frequency is 6 Hz. So if the lowest frequency that can be measured is 42 Hz, then what is the value of the damping ratio that is being asked? So we saw that the expression for z by y was equal to r square upon root of 1 minus r square square plus beta r whole square. So this is the general expression for z by y. So here we have been given that the error in the measurement, it is 2%. So then in that case, so basically we have been given the ratio z by y. So it will be either 1.02, considering 2% error, or it can be 0.98. So it should be either 2% greater or 2% lesser. So let's calculate with 1.02. So here we have been given omega is 42 Hz and its natural frequency omega n is 6 Hz. So R is basically 42 by 6, which is 7. So then, so we have basically 1.02 is 7 square upon square root of 1 minus 7 square the whole square plus 2 into zeta into 7 2 square. So if we, so we have to basically solve for zeta. So then we will get 7 to the power 4 by 1.02 whole square minus is equal to basically uh, so 7 square will be 49 and 49 minus 1 is 48, so basically 48 square plus 4 into 49 into zeta square. So if we solve this for zeta, what will be the value of zeta here? Can someone tell me what is the value of zeta square that we get? So I got 0.1386 or nearly 0.14. C is the correct option. So now if you actually
No.
try to solve it,
I have a question for that.
yeah,
We have taken 1.02, okay,
right,
that error.
yeah,
Sometimes we have to take 0.98.
right.
So how to decide that which one we should take, 1.02 or 0.98?
Right. So for that, so we have, so we are not assuming any specific system characteristic like under damped or over damped or anything like that. So we are generally just calculating what is the response. So basically the damping, whatever value that we get, it should be some real value, right? So zeta should be something non-zero and real value. So suppose like if we solve again with 0.98, we will see what we get. So we will see the damping value that we get with that.
No, I think we should we decide from some graph that whether we should take 0.98 or some 1.02, that error.
Yeah, so if it
From
is, yeah, right. So if it is a vibrometer, then the value of
Z upon Y.
yeah, so z by y, it should be something which is close to 1. So it should be either, it will be, so when it is close to 1, it can either be slightly more than 1 or slightly less than 1, right? So physically, so it actually they are more or less equivalent, right? So like 0.98 or 1.02 as such, they
No,
are
no, but if we take 0.98, then we may get a different answer. And that if the answer is in that option, suppose, then which one is the correct? Other way, whether we should take 1.02 or 0.98. Suppose if we had taken 0.98 and the value comes around for 0.5 and something like that, suppose. So that is also their option.
So sir, then
Hmm.
I think you can select both the options like in that case. So if that is the case, because
Okay.
actually there is no specific thing as like z by y
No,
should be
this is my first time, sir, attending this NPTEL classes, and may appear for the examination also.
right.
Okay, whether the formulas will be provided to us, or what?
Uh,
Because we have to remember it.
Actually, I am not sure about this part because I am not actually managing the examination
No, no,
part
not like that. Okay, okay, no issue.
because
No.
I won't be able to actually answer this specific query
Huh,
because
huh.
I am not handling
Because
sir.
this is my first time, na. That's why I
Right,
don't
right.
know, because remember the formulas and all these things, na, difficult, है ना?
Yes, yes. Yeah,
Because
definitely, definitely.
n number of formulas are in this vibration.
Yes, yes.
Okay.
So I think
If
you can actually so you can post this question in the discussion forum for the course, sir. I think that would be better. So then one of the TAs or the
अच्छा,
professors can answer this
hmm,
because so they will be actually managing the exam part. So
अच्छा, अच्छा,
so that would be better. But I think
hmm,
generally they should allow you to carry some formula sheet with
hmm,
you,
hmm, hmm, hmm.
like maybe one single uh, page A4 sheet with all the
अच्छा, अच्छा.
formula written. So that's how generally we have been doing in my institute. So
Because formulas are no doubt at all, formulas are important, but though we have formulas that are our disposable, then also difficult to find the answer of this that question. है ना?
right.
Hmm. ठीक है.
So sir, did you try solving with 0.98 as the assumption?
I can do now.
So can you sir just try and tell me?
Yeah, definitely, sir. You take another problem, no doubt, no problem.
No, I am actually solving here as well. Uh,
Hmm.
so if you can just check and confirm what is whether whatever I have done is correct or not. So I actually get zeta square is equal to 1 here.
Hmm. Hmm. Hmm.
So if we assume it as 0.98, so then we will get actually
Hmm.
zeta square is actually 1. So here,
Hmm. Hmm.
uh, if we want to uh, measure some vibrations, like if
Hmm.
there are oscillations in the system, then zeta is equal to 1 is basically critically damped, right sir? So then there will be no
Hmm.
oscillations in the system.
Hmm.
So if the system is critically damped, it will be having some displacement
Yeah, yeah,
profile
yeah.
like this, right? It will
Uh,
be
uh,
rise
uh,
to
uh,
some value and then again fall off. So then there
uh,
will be no oscillations. So then this is not
uh,
desirable. So then we can actually
hmm.
discard.
Hmm.
Now if we had got some value which is like greater than 1,
Hmm.
so then again it will be the same, like it will be over damped. So then there
Hmm.
will be no oscillations. So again that will be get discarded, right sir?
Hmm. Hmm.
So that's the overall in. So now let's move on to accelerometer part.
Mm.
So the system as such and the setup will again remain the same. So we will again use the same uh, setup of Z by Y and Z.
Seismometer we can use as a for displacement measurement, for velocity measurement, as well as for acceleration. Is it correct?
Seismometer we can use for displacement measurement definitely. So
Hmm.
if we want to use it for acceleration measurement, then we'll have to correct the value like reading as per whatever the value of r and zeta and whatever that like basically
That values will change. Otherwise, the setup will remain same.
the setup is same. Yes.
Huh.
So when we are using an accelerometer, what essentially is happening is that uh, we are using a very stiff uh, thing with a very small mass. So it will be very small in size. So it will have a very high natural frequency. So because it is used as an accelerometer when omega by omega n is much smaller than 1, or so it has a very high natural frequency. So then uh, so in that sense accelerometers are in that used in that range. So in this question we have been given that a vibration measuring device is used to find the acceleration of a machine running at 200 rpm. So if the natural frequency of the instrument is 10 Hertz and it shows a displacement of 0.006, we have been asked what is the acceleration reading. So here, so we have been given omega is 200 rpm. So basically that is the oscillation frequency or basic excitation frequency. So which is basically, so if you want to convert it into hertz, so we will have to multiply it by 1 by 60. So if you want to get it in terms of hertz or cycles per second, so which is 20 by 6 or 10 by 3 hertz. Whereas omega n is 10 hertz. So here r, which is omega by omega n, which is here 1 by 3. So we have the usual setup of Z by Y is r square upon so in the accelerometer what we would have is that Z is proportional to the y double dot basically, or so for accelerometers. So then omega n square z, so r square if we bring it on to the left hand side, so it will be omega square y should be equal to this thing. So then omega square y is basically the amplitude of y double dot. So it's the amplitude of the acceleration of the base. So for this for the accelerometer, so when r is much smaller than 1, then this value of this expression would be nearly equal to 1. So then we have been given that z is basically 0.006 centimeters. So if we find out z by y is, what is the z value of z by y? It will be, so here, since there is no mention about anything related to damping, we will assume that zeta is equal to 0. So then it will be r square upon root of 1 minus 1 by 3 square whole square, so which is 1 by 9 upon 1 minus 1 by 9, which is 1 by 8. So z by y will be 1 by 8. So y will be 8 times z, which is 8 into 0.006 and omega square y will be the actual true acceleration that will be measured, and that will be, so what is the value of omega square? Omega is basically 10 by 3, so 10 by 3 whole square into so this has to be actually converted into radians per second. So so it is 2 pi into 10 by 3 omega square into 8 into 0.006. So it will be something about 21.06 centimeter per second square. So this will be the true acceleration. But now if we assume, do the accelerometer approximation, that omega n square z is the acceleration reading, then we will get 0.006 into, so omega n square is 10 into 2 pi, so 4 pi square into 0.006 into 100, so which is 2.4 into pi square, which is approximately 23.69 centimeter per second square. So approximately, like we can say that this would be the accelerometer reading. So because the value of r is 1 by 3, which is not, which can be actually further smaller than 1, so that's why we get some difference between this approximation of omega n square z and omega square y. So any questions?
No, no. I think the same formula is required, no? X upon y.
Yeah, so for these type of problems, it's like mainly the same formula. We can just so largely it is based on the same setup and same system. So sometimes basically so when it is used as a vibrometer or accelerometer, depending on the instrument, so we have the values of the things that will be changing, but essentially the setup is same, so the equation is also same for that.
Mm-hmm. Okay, sir. I will do these things. Huh? X upon y if it is there.
So we can
Operating system.
here we again have this similar kind of example where just now whatever we discussed. So so we have been given that like let us say if we have an accelerometer that has a suspended mass that is given, it is mounted on an engine which is undergoing an acceleration. So its true value is 9.81 and the measured value is 10. So so basically we have to find out what is the value of the spring stiffness. So we have to find out basically for that the value of r. So we have been given that damping ratio is 0. So we have been given the value of omega as 6000 rpm. So which is 6000 by 60 into in terms of hertz, which is 10 hertz. Sorry, 100 hertz. And then so we again apply the same concept of z by y. So which is r square. So now like which is omega by omega n whole square. So here because zeta is 0, so we can just write 1 minus r square. So basically the omega n square z will be whatever will be the measured value of the acceleration, and omega square y will be the true value of acceleration, that will be 1 upon 1 minus r square. So measured value will be 10, and the actual value is, let us say, 9.81. So 1 upon 1 minus r square is this. So we can find out what is r square. So it will be 9.81 by 10. So 1 minus 0.981. Just we get about 0.14. So basically then 0.13, so something like 0.1378 or something like that. So omega by omega n is this. So and we know omega is
6000.
yeah
That
6000
is
or 100 hertz.
100 hertz.
Yeah. So omega n will be 100 by
0.1378.
so this will be in terms of hertz. So in terms of radians per second, it will be like this. So this will be basically root k by n, omega n, and we have been given that the mass is 0.01 kg. So omega n we will get so using this value we can get basically the value of k. So it will be m omega n square, and from that we can basically calculate the value of k. So this is the general scheme of things, like so it's basically the same formula and the same setup that will be applicable. So depending on what the system is, we will get so either the acceleration, either used as accelerometer or vibrometer.
The only thing is that we have to remember that omega upon omega n should be how much,
Right.
that
So
ratio.
yes, if it is used as a vibrometer, then the omega by omega n value should be large,
Greater than equals to 3.
3, right? And for the accelerometer,
It is very, very less than 1.
yeah, it will be very less than 1.
ठीक है.
So just
ठीक है
just, just
सर.
the basic concept is just that much.
हाँ, thank you.
So I have some more problems, but they are like very similar. Like it's just uh, the same formula being applied again and again. That
Oh, oh, understood, understood.
so you can actually try out those
Hmm.
problems.
No issue.
So any doubts?
No, sir, there is no any doubt. No.
So nowadays,
Please,
yeah, yes,
yeah, yeah, please. No, please share me that your email ID, but
yes, yes, yeah, that I will
Hmm.
share.
Okay.
Sure. So as such, from problem solving part, I'm that's all that I have from my side. So in like nowadays, sir, we have like our all smartphones. They also have accelerometer and gyroscope sensors in them. So
Yes, yes.
we can actually use these smartphones also to do some experiments in vibrations.
Hmm. Hmm.
So in one of the I think first or second uh, live session, I think second live session, I had just introduced a small activity using smartphone based accelerometer. So you can actually check out that set. So
Acha.
you can actually think of that in your college as well. So so students will also find I think that very interesting. So
Acha. It is in second, na?
yeah,
Second
it is
week.
second line session. So
Huh.
so
Okay.
we can use our smartphone itself. So we don't need to buy even like any sensors. We can just install some apps which
Hmm.
can do sensor data logging in the smartphone itself, and then we can export that sensor data to Excel or whatever format, and then we can then process that data to and do FFT or whatever analysis, and then we
Hmm.
can actually get the frequency content of the signal. So I think then that you can actually think of implementing, sir, like if you want, if you are thinking of any
Sir,
track.
I have one different query. How this vibration part helps to your PhD work?
Not exactly. It's
Hmm.
just it's not exactly related to my PhD work.
Hmm.
My PhD work is more related to controls, uh, dynamics and controls in vehicles. So it's not exactly related to my PhD work.
That I think. So you are preparing this or this particular vibration area or for this NPTEL or
Right.
something. Acha,
Yes.
acha. It is assigned work to you. Is
Yes.
it
Yes.
so?
I've been assigned. Yes.
Acha, acha, acha. Okay. No issue. ठीक है sir. Thank you.
Sure, sir. Yeah. Thanks.
Hmm?
I think we
Thank
can
you.
end our today's session here.
Yes, yes.
Thank you for attending.
And don't forget to send me that mail. Huh?
Yeah. So
Okay.
I will share
Send.
it right now in this chat itself.
Acha,
In case
acha.
you don't receive it, I will email you whatever. Uh,
Okay,
I'll just
I
send
will
a
write it down. I will write it otherwise.
yeah.
You send it, I will write it. Just a minute.
So have you noted down, sir, the
Yes,
list?
yes, yes.
Which,
Thank you, thank you.
sure. Thank you. Sure.
Okay,
Then we can end the session for today.
okay, thank you.
Thank you. Yeah. Good night.